Hi there, I'm Andy Rudoff. I work on persistent memory at Intel. I'm also a charter member of the SNIA NVM programming technical work group, where we published the persistent memory programming model that I will be referring to today. I'm also active in the Compute Express Link or CXL consortium, and I'm going to be talking about all three of those things today. Typically at these summits, I'm the guy who talks about what's happened with persistent memory in the last year and how did we get here. And so that's exactly what I'm going to do, hence the name Persistent Memory Today. In this talk, I'm going to talk about the story so far, just a brief history of how we got where we are today. And then I'm going to cover a somewhat surprising focus that PMem has had in the past couple of years, and give you a few examples of that. I will talk about how people ended up using the programming model and what are some of the most modern usages of persistent memory. And then finally, I'll end up by talking about the future directions of persistent memory and where I see that going. Okay, so let's talk about the story so far. All right, around the time that I indicate on this timeline, NVDIMMs were emerging. They were already in the market. And NVDIMM-N in particular, I took this picture from the SNIA website. NVDIMM-N looks like this. It has DRAM on a DIMM, and when it loses power, there's some stored energy, and it squirrels away its contents. So the DRAM is obviously not a persistent media, but this presents itself as persistent memory, and it's very much the exact model of what we were aiming for when we formed the technical work group around it. So with that in the market, we were able to use that to kind of everybody interested and the OSs interested. We started the technical work group, and it was kind of instantly popular. OSVs, ISVs, even the hardware vendors joined us right away. And because that interest happened, we had our first persistent memory summit in January of 2013. Actually, it was called the NVM Summit back then. It was very much the summit, the same summit that you're attending today. We've done it every year since then, indicated by these little crosshatches here. And they've been a lot of fun. So with all that momentum, we pulled together our first version of the spec. It covered multiple types of non-volatile memory programming, but system memory was the main focus. And the 1.0 spec was published there, as you see, in 2013. After some more work in mid-2015, we published a revision of it, 1.1. And then finally, we published 1.2 in mid-2017. And after that, kind of ran out of things that it needed. It seems to be holding together. It seems to have driven the software development that we were hoping for. And so we have not worked on publishing a revised version of this spec in the past few years. Of course, we can revisit that if the need arises. So far, it's actually been holding together pretty well. Now, during this time, these NVDIMMs were the only commercially available persistent memory. Then in April of 2019, Intel's Optane became generally available. And so now there's multiple persistent memory products in the market. For those of you who might not be familiar with Intel's Optane, I'll do a very quick description of it here. Here's a picture of the DIMMs on the left here. And this green path here, which marketing has called the app direct path, this is the persistent memory programming model. And I kind of show a cartoon version of it on the right, where an application can memory map persistent memory and do loads and stores and expect a latency of about 350 nanoseconds. And when you have direct load store access to persistence like that, it opens up some possibilities, but also some kind of tricky programming. So we saw the need to introduce some APIs to help out with that. I'm going to cover that more in a moment. But before I leave this slide, I wanted to point out that the product, because of its large capacity and price point, it was believed that it would be popular not only for the persistent memory programming model, also just for its capacity. And that's what the left-hand side of this diagram is for. It's a two-level memory or a hierarchical memory. The marketing name became memory mode. And the idea here is that when the processor accesses memory, it first looks in your normal DRAM as a cache. And when you miss that cache, it goes and looks in the volatile configured persistent memory. So this idea that persistent memory can be partitioned into half of it that's used for persistence and part of it that's used for volatile capacity, that's carried forward. And when I get to CXL, you'll see that that became part of the CXL standard. So we kind of have learned as we've gone along here. So during this time, back to the timeline, all the operating systems, the major operating systems, were looking at the programming model and deciding what needed to happen here. And so I wasn't sure of the exact year that these implementations became usable, but by the time the Optane shipped, the three major OSs, Windows, Linux, and VMware, were all supporting it. In fact, they were all supporting not just persistent memory on the bare metal, but in guests, like in a Hyper-V guest or a KVM guest or obviously an ESXi guest. You could get that programming model inside the guest and get direct access to the persistence. So that was pretty cool. And so again, we knew that just exposing that to user space wasn't quite enough. So we started on the persistent memory development kit. Now we actually started very early on this, and I'm kind of skipping a bunch. About the time that some of the OS work was viable, we released 1.0 of the persistent memory development kit. So that was somewhere in 2016. When I went and looked at where it is today, that same set of core libraries is up to 1.11.1. That doesn't really capture all the development that's happened in those years, because a lot of additional libraries have been added, and some of them have their own versioning schemes, in fact. Just to give you a quick picture of what that looks like, this slide kind of grows more boxes every time we put it together. You can see over on the right is our programming model. Here an application is mapping persistence. And don't think of PMBK here as an API that you have to call for every access. The whole idea of giving an application direct access drove the design of a lot of these libraries. Our most popular library, libpmem obj, which is architected by the PMBK lead architect, Piotr Balcer, is designed in a very clever way that allows you to do things like allocations and transactions, but still do kind of normal language operations like dereferencing pointers and so on to get to the data. So it's a kind of a very different sort of a library than you would expect from, say, a storage-oriented library where everything is buffer-based, where you pass buffers in and out. PMBK has a few of these transactional libraries, and they have these different language bindings that you see across the top, C++. There's a low-level persistence library that's for Java. There's actually a very recent library for Java, PMUL. It's actually kind of exciting. It's coming into its first release. So if you want to know more about that, you might take a look at it on pmem.io. And there are other APIs like a key value store and some low-level libraries. Now, we learned so much in the early years of these low-level libraries doing libpmem, it evolved into a libpmem2, which we now recommend everybody use. And it's much more convenient set of APIs for people. We also had a librpmem, which was for remote persistence memory over RDMA. And frankly, we learned so much from that we decided to sort of do away with that library and tell people to stop using it in favor of a replacement library that makes a lot more sense called librpma. And when I talk some more about RDMA, some of those solutions that I talk about are using librpma. So that's pretty exciting. And then finally, there are some volatile use cases, as I mentioned before. People like to use the media for the fact that it's a very large capacity. And so there are a couple of these volatile things. PMem.io has a link on it to a book that's free to read online. It describes these APIs, it tells you how to use them. So I won't go into it any further, but a lot of the current use cases where I see people using persistent memory, the majority of them are using PMDK in one way or another. So back to our timeline. Now in 2019, the Compute Express Link 1.1 spec came out. And then sometime a little more than a year later, 2.0 came out. This is where I got involved with CXL. And I got involved to add support for persistent memory. A bunch of us took all the learnings that we got from these earlier years and rolled them into the specification, so that in CXL, now all of the things that we learned about using persistent memory are now part of an open standard. CXL talks about these representative device types, type 1, type 2, type 3. Well, type 3 is how you add memory to a system, and that's where we see persistent memory being added. Now, it turned out, of course, as we went to go add mailbox commands, management commands, and things like that to CXL for persistent memory, a lot of them made sense for any kind of memory. So a lot of the work that we did turned out to be generic across all types of memory, persistent or volatile. But there is still a good amount of changes that we made that only apply to persistence. So that all went in the 2.0 spec. And then finally on my timeline, I should mention that we continue to build on that, and the 3.0 spec is coming out pretty soon. I didn't attach it to my timeline here because I'm not quite sure of the date where it's going to be released, but it's in the next couple of months, I think, give or take. So be watching for that. There's a lot of pretty exciting stuff building on top of the 2.0 spec, and a lot of activity on that. I'm going to talk a little bit about more of that in a minute. First, let's talk about now how all of this came together as a programming model. And the programming model has a lot of aspects to it, but really the single most important thing is this idea of direct access, or DAX, as we abbreviate it. You can see I took these slides, I ripped these slides from all the previous Persistent Memory Summit presentations where I talked about the programming model. And it went through a lot of variety over those years. The DAX was really the main focus and the one true thing that we wanted to make sure we got into. All of the operating systems, and including when you're running a virtualized guest, you want to be able to do this direct access. And I'm happy to say that that has worked out very well. So now let's talk about the use cases, especially how in recent years there's been sort of a surprising focus. I'll tell you what that is. Whenever I talk about the use cases for persistent memory, I like to divide it into these 4 quadrants that are all 4 fairly popular. On the left are the persistent use cases. These are the use cases that actually leverage the fact that the media is persistent and maintains its content across power loss. On the right are the volatile use cases, where the use cases are using the media for its cost or for its capacity, but ignoring the fact that it's persistent. The top 2 quadrants are non-transparent. It's where applications have been modified to specifically know about and use persistent memory. On the bottom are the transparent use cases where the applications have not been modified. So these 4 quadrants, all the use cases that I talk about fit into one of these 4 quadrants. So it's always good to throw up this slide just to help focus what, when we're about to have a conversation on one of the use cases. In this case, I'm going to concentrate on the right-hand side where we're ignoring persistence for a moment. We're just using persistent memory as a tier of memory. So I would call this use case memory tiering in kind of generic terms. And again, it can be either transparent, where the application has not been modified, or non-transparent. So let's first talk about the transparent use cases, which have, this is the surprise that I was talking about. We always knew that this was going to be interesting, but actually, frankly, I have to say I'm surprised at just how popular this is. We have quite a number of these use cases now. Let's talk about all the different ways that you can do transparent memory tiering. This is an incomplete list because there's actually quite a bit of work going on in this area. I already mentioned memory mode and talked about the picture, and this is done in hardware, so it's transparent even to the OS, well, mostly. And I say that because we did end up making changes to the OS to enhance it, to manage it better, to handle errors and things like that. If you booted an OS that didn't know about this, it would work, but it's better with the changes. Another one of these is done completely in the kernel, and in the Linux kernel, I would call this Linux kernel memory tiering. This went upstream recently within the past little over a month, I think. And again, I say mostly because I see a lot of ongoing work happening with this to continue to refine it, continue to build on it. Plus, just going up into the upstream kernel on kernel.org doesn't make it easy for everyone to get to. It has to flow down into the distros, and that's still happening. This picture on the right is really the same programming model, but with a sort of a Linux angle to it. You can see that Linux added something into the programming model that we didn't specify in the SNIA document, and they call it device stacks. And it's this green box over here, where the persistent memory can appear, instead of a file system, it appears as kind of a raw device, and applications can open it and map it just like they can files. But Linux then did something even more interesting with it. They allowed you to configure this device to make it part of the system's main memory with its own distinct NUMA zone number. So now you can use APIs like libnuma to allocate normal memory and this memory as you see fit. And once you have this memory appearing as a NUMA node, Linux has this feature called auto NUMA, which you can build together with that. And that migrates pages that are hot to the lower latency zones and pages that are not so hot to the higher latency zones. And so that together is what really makes up this Linux kernel memory tiering. So keep your eyes on that, because I think it's actually going to continue to evolve and become fairly interesting. Over the last year, VMware also announced a memory tiering project called Project Capitola. It's in technology preview right now. I took this picture from their blog, and you can see its goal is to aggregate tiers of different types of memory. Just as VMware virtualizes lots of hardware and alleviates people from having to worry about all those hardware differences and just run things in a kind of a managed guest environment. That's the same idea here, where they manage the tiering of memory. So hopefully alleviating someone from having to configure all these different modes or different types of memory tiering. So again, we have some pretty high expectations for this. It's looking pretty good from the technology preview. So it's something to keep an eye on. And then MemVerge offers a solution that's done in user space. I took this picture off their website. It's got a lot of boxes, but basically it's showing that MemVerge can interpose itself between applications and the operating system and transparently do memory tiering. And I have to give MemVerge a special shout out, because not only do they do memory tiering like that, but they found some pretty interesting ways to leverage the persistence, taking some very powerful snapshots of your application state and so on. If you want to learn more about that, tomorrow, Charles Fan, the CEO of MemVerge, is going to give a talk called Persistent Memory Breaks Through the Cloud. So keep watching in the summit to learn more about that. Okay, so those were transparent. Now for the non-transparent version, this is where the application gets modified. And I just have to point out that the term application kind of needs quotes around it, because if I modify, say, a key value store like Redis or Cassandra, the people calling it don't get modified. Which one of those is the end application? Certainly something in user space has been modified, but the users who are using those APIs didn't end up modifying anything. So in a way, it's a matter of perspective, what gets modified. These solutions where user space code gets modified often perform the best, because they can make some informed decisions about data placement. The architect of one of these key value stores probably knows better than any heuristic what's going to be latency sensitive and what isn't. And so it can oftentimes outperform the heuristic-based solutions that are done in lower layers. Another thing that's important and that we've seen a lot of success with is combining these solutions. So you can combine these transparent solutions with the non-transparent solutions. For example, if you use libnuma to give the operating system hints about what your data placement, you can use that in conjunction with Linux memory tiering. Or MemVerge has an API that it's optional for an application to use, but if you use it, you'll get better performance. So there's a lot of memory tiering stuff going on here. This is a very active area. This afternoon, Alessandro is going to give a talk called Making Sense of Memory Tiering, so you can get a deeper dive on this. So I'll leave it at that. but I think that the success of the memory tiering with persistent memory has been a pleasant surprise and has been a very popular use case. Okay, so now let's go on to the actual use of the programming model and the persistence part. So that's the left-hand side of my 4 quadrants. Now, in the lower part here, where it's transparent to applications, this is really just the storage APIs, right? In our programming model, we always draw some sort of driver here that talks to persistent memory, and it provides the storage APIs to unmodified applications. So if an application wants to open up a raw device, or if it's just using an unmodified file system, it works, and this driver takes the block IO, read a block, write a block, and converts that into persistent memory operations transparently. So I have seen a lot of these use cases happening over the past few years for very latency-sensitive storage use cases, like a latency-sensitive database log is a good example, or the memverge example that I mentioned earlier. But really, it's the right-hand side of this diagram where you get the biggest bang for the buck, and that's where you decide, I'm going to modify the application to really use DAX directly and leverage what persistent memory can do. Our poster child for this has been Oracle. We had them at the PMem Summit in recent years, and I actually grabbed a couple of their slides because I wanted to point out a specific aspect of what they've been doing, and that has to do with RDMA. Notice how prominent RDMA is on both of these slides. You can access persistent memory like memory. It sits on the memory bus. So DMA works. It means RDMA works. It can be remotely accessed by the RDMA protocol. In recent years, we've been driving changes into the standards bodies to make RDMA aware of persistence, to improve these use cases even more. And we've seen a lot more activity around RDMA with persistence. And I mentioned earlier, there's this new library, librpma, as part of the persistent memory development kit to help. So RDMA is one of the areas where we've really seen some growth here. Incidentally, there's more about Oracle in a talk this afternoon that VMware is giving. So you might want to watch that and hear more about it. So I went looking for RDMA related use cases, and I found this Tencent use case. You can see from this slide, I'm not going to go into all these details. It's a little marketing-ish, but the technical parts here are clearly some significant improvements in latency on both the write and the read paths. It does use RDMA. I've put a URL here on the bottom, so if you grab the slides and want to read more about this, you can click on the URL and read about how Tencent has used persistent memory with RDMA for cloud storage. So that's kind of an indicator of how somebody can build on our programming model. They can use features that persistent memory supports, like RDMA, and build on that. And this is, I tried to pick a recent example to show that these use cases are still very much actively emerging. I found another one, which is this Baidu use case. Again, they brag about a 10 to 20x increase, which is awesome, right? And in this case, there are 3 things I really wanted to point out about this slide. And again, there's a URL on the bottom if you want more detail. One is that it's built on PMDK, and again, we've seen a lot of our current use cases leveraging that just to help with a lot of the trickier programming and hardware detection, cache flushing, stuff like that. But notice there's another set of libraries here that uses SPDK, which is the Storage Performance Development Kit. SPDK is a popular set of libraries for creating high-performance storage appliances, for example. And SPDK and PMDK work well together, and they have in this use case too. So I think that's a good indication that there's a lot of tools out there to help people use persistent memory. Finally, this is kind of a very deep nuts and bolts detail on the slide. There's an instruction on the Intel processors called CLWB that is used to flush writes back to persistence. So this improved in performance with the Ice Lake processor and beyond, and these solutions just get faster without them having to recompile or rebuild or anything. So, keep on the watch for those kinds of enhancements generation over generation, because I think they're going to continue. Okay, let's talk about the future directions in the time I have remaining. Compute Express Link, right? We think that CXL and PMem are just made for each other. It's a really great match. There's a lot of energy here. I presented on it last year at SDC, and this was my summary slide. And I put it up here because I just really want to drive home this first bullet here. The programming model for persistent memory is the same. If you have a program that uses persistent memory today, the same binary will be able to use persistent memory on Compute Express Link. There's no change to your program. There's not even a recompile, right? Because we kept the programming model exactly the same. CXL offers moving that persistent memory off the memory bus so it doesn't steal bandwidth away from your DRAM when you're accessing persistent memory. That's pretty exciting, we think. It gives us a lot better scalability, not just for persistent memory, but all types of memory. And added flexibility, I would say. It's an open standard. It has the standard includes ways of managing this memory. It's got flexibility for configuration like hot plug, things like that we could really never do with the DDR slots. And as I mentioned before, all this support for PMem has gone into the 2.0 spec, but there's some exciting stuff coming. If you want to hear more about it, see Al and Benjamin's talk tomorrow about CXL. I think he'll even give you a peek to some of the stuff that's coming in the 3.0 spec. So pretty exciting. So where do I see some future directions going? I'm seeing a lot of work around artificial intelligence and machine learning. People are figuring out how to really leverage persistent memory in those cases. I actually found an interesting blog here by Allison Goodman from Intel's Optane Group, so I put a link to it here. It tells you more about it. As I mentioned before, I'm seeing a lot of people leveraging what RDMA can do. Storage solutions are storing metadata in persistent memory because they like the fact that it can read and write at any size instead of blocking that metadata into block sizes. And of course, our in-memory databases, the SAP HANAs of the world and the Oracle and so on, these are still our classic use case. I think SAP HANA was the first use case that we talked about publicly, and we're still very, very happy to see that continue on. For other future ways that PMem might be used or accelerated, you might take a look this afternoon if there's a talk about using that some hardware offload from Ziya Yang, and I think that'll be pretty interesting. Okay, so that was sort of a whirlwind tour of system memory today. I hope that you found it informative. Please take a moment to rate the session. We do listen to all the feedback, and thanks very much for watching. I hope you enjoyed it.